Okay, welcome back. We're going to put our two results together. Again, we just got the contribution to the current source we showed was to Vx was negative 5.349 volts approximately. Not a nice round number. And then from before, to remind you, we got a contribution of negative 1.5 volts when we only have the active voltage source turned on. We're going to add those together. So we've got this plus negative 1.5 volts. And that gives us approximately negative 6.849 volts on the circuit Vx. On the resistor R6, or as drawn voltage Vx right here. So it's drawn with the positive end here. So what we're saying is that the difference from here to here, this is at a higher voltage, and at least according to our calculations, it's 6.849 volts higher than this terminal. That's why we're saying it's negative. So right here, where the test asks us to fill in the voltage Vx, we've got negative 6.849 approximately. Also determine R7 such that the output of the op-amp Vout has a magnitude of 1 volt. And we're assuming that the op-amp is ideal. Okay, so to continue solving this, I'm going to go out on a limb here. Again, we're going to need to know this voltage because it forms the input into this op-amp, and we need to figure out what R7 is going to be so that Vout is at 1 volt. So we definitely need to know this input voltage. So how do we do it without replicating a lot of work that we've already done? Well, if we go back to our original, when we turned off the current source I2 and just had the voltage source V1 on, we came to a conclusion that doing our loop analysis, this current IA going through here is actually equal to 1.5 milliamps. So if that's the case, then what we can say is, don't lose anything here. So what we can say is, so we've got 1.5 milliamps flowing through there. We have for V2 give that a shot. So let me get some new paper here. So here's our equation, our last known equation for V2. We had discovered that we know what IA is. So V2, come on. V2 is equal to negative IA, which is 1.5 milliamps. 1.5 times 3 times 1K. The 10 to the minus 3 and the K cancels, so we've got negative 1.5 plus 4 times 1.5 is 6 times 3 is 18. the 10 to the minus 3 and the 10 to the third with a k cancel. So we've got negative 1.5 plus 18, which gives us a nice 16.5 volts. Again, assuming all my units cancel appropriately. So now that gives us a value for V2, 5 volts. Well, since we know this current right here, which is 1.5 milliamps, we know that we're going to drop voltage right here of 1.5 milliamps times 4 times 10 to the third. So the voltage drop there is going to be 6 volts. So if this is at 16.5 volts, this terminal up here must be at 6 plus 16.5, or 22.5 volts. So that's going to contribute to V1. Now that's just from this active source. So let's to our current analysis when we turned off the voltage source and we just turned on the current source I2. So when we turned on the current source I2, we did almost find out what VC was. Remember that V1 right here. V1 is actually right here, just in between the two. I'm sorry, not V. We need VC. Strategy. If we look at the redrawn circuit here, we're at ground here at 0 volts. We're going to work backwards, so we can figure out. We figured out what Vx was. Our ground contribution from Vx was right here. It was the difference just from this current source was minus 5.39 volts. So if we can figure out the drop here, and then we can add 5.39 volts, and then we can subtract whatever this voltage drop is here, we'll know what this voltage is here. So let's do that. Again, from the redrawn circuit diagram. So we're at 0 volts here, 0 volts here. You know the current IB. So to figure out what the voltage is here, we go. So let's call this Vx. No, I can't call that Vx. Let's call it V alpha. So V alpha minus V. The current in this direction up. So it's because that's a resistor. So the voltage drop. Okay, so actually V alpha is going to equal to IB times 2K. We had decided by looking at this diagram, we knew that 4e minus 3 Vx had to equal IC minus IB. We solved for IB and we said IB is equal to IC minus 4e minus 3 Vx. Again, we had decided that, or we had solved the contribution that Vx had to be negative 5.39. So, and that IC is 2 times 10 to the minus 3 amps. So 2 times 10 to the minus 3 minus 4 times 10 to the minus 3 times negative 5.349, which is equal to, I'll just plug that into the calculator. Alpha has to be let's call this 23.4 times 10 to the minus 3 times 2 times 10 to the 3. 10 to the 3's cancel. This is approximately equal to 46.8 volts. So we add 5.349 to this. We're at 52. That, and so to figure out this voltage difference, we will take just the current IC, which we know is I2. So it's 2 times 10 to the minus 3 times the 2K resistor, 2 times 10 to the 3. These powers cancel, and we're left with 4 volts. So this point is 4 volts higher than that. So we've got to subtract 4 volts from here. And we're left with 48.149 volts as our input V1 to the circuit. So here, again, now this is where our knowledge about op-amps here. So I'm guessing that we are right here, we're at 48.149 volts. That seems awfully high. I'm guessing it's incorrect, but let's just leave it at that for now, and just figure out how this works. We can redraw this circuit if you really want to understand op-amps. Look at it this way: we've got a V out right here. Then comes the resistor R8. Then comes the resistor R7, and then ground. And we know that at this node right here, this is what actually is going into the op-amp. And this is at ground as well. So what's happening here is we've created a voltage divider to actually this this is not a ground, excuse me. This is where our V1 equal to 48.149 volts is. We've created a voltage divider. Since we've got negative feedback going in here, the voltage is always going to climb until it tries to settle itself. So if this is lower voltage than this is going to increase V out. If V out increases, it will increase this node. And so basically, this is going to work to try and create an equal voltage here. So it's going to try to make this voltage actually equal to the input. We know that VW has the voltage divider, so it's V out times R8 over R8 plus R7. And we know that that has to equal the 48.1 or whatever other value. The question asks us to determine R7, but it tells us R7 is 1K, so I'm guessing this is a typo, and it wants us to find R8. So all we've got to do is we want V out to be 1 volt. So our equation becomes R8 over R8 work out the equation. R8 equals R8 times 48.149 plus 48.149 times 1K. Subtract from both sides, so factor out, divide 48.149 over 1 minus 48.149. This gives us a negative value. Clearly, I did something. You got the process by which to do this. Hopefully that helps. Maybe I'll try again later. Good luck.